and everything else in the universe is made out of particles. My name is Andrew Sada. I'm a junior in Salisbury School, and I'm going to be talking about particle collision simulations. So what am I doing? It's, as the title says, I'm simulating particle collisions. Why is this important? Well, first of all, we want to understand the universe, and we need computers for that. We need to know everything. We need to know every single concept. I'll get back to that later. So, what are particles? This is the standard model. We have our quarks, up quark, down quark, top quark, bottom quark, charm quark, and strange. Then we have our leptons, electron, tau, and muons. Then we have their neutrino counterparts. And then we have our gauge bosons, the gluons, photons, W bosons, and Z bosons. Then we have our Higgs boson. Everything you see is made of quarks. Everything is made out of quarks because quarks make up protons and neutrons make up atoms, and atoms are the basic building blocks for everything. So in physics, we describe particles as three things: an excitation of a quantum field, a collapsed wave function, or just pure energy. So, for example, let's take photons. Photons are an excitation of the electromagnetic field. When there's a point of high energy in that field, that's where a proton is. Then we have the Higgs field. The Higgs field is important because it gives quarks mass, it gives electrons mass, but that's it. That mass only accounts for about 1% of matter in the universe. So why is this 1% relevant? It's relevant because, let's say for example, an electron didn't have weight because the Higgs field doesn't exist to interact with it. The electron is a fundamental component in an atom. So if we can't have atoms, we can't have anything. So what are particle collisions? Basically, in the LHC, the Large Hadron Collider at CERN, we take protons or neutrons, any hadron, and then we spin them around using electromagnets and electric fields, condensing the electric fields into condensed electric power, basically boosting the particle up to 99.994% the speed of light, where then they will collide and create other particles by breaking themselves down. Then we have supersymmetry. Supersymmetry was a theory to fix the mass of the Higgs boson and fix the cosmological constant problem. Supersymmetry essentially says that to every particle on the standard model, there is a supersymmetric counterpart. So why do we need to understand these concepts? These concepts apply to everything in life, but in important fields like energy, these are especially important. Nuclear fusion depends on knowledge and concepts about strong, weak forces, how quarks behave in order to generate energy. So, how does this affect us in the near future? Recently, people have been using charged nanoparticles, iodine nanoparticles, to trigger cancer cell death. This is still in research, but just imagine what you can do with that. So how are simulations a part of this? So the simulation I use was Pythia. It's an integration-based program, which basically it generates high energy events or collisions, and then it will give you the particles that come from it, the energy generated from it, and the total mass. So what purpose do simulations serve? Well, we use simulations as the current model of our understanding, the standard model. We can change these parameters in the simulations whenever we want. So, right now we use simulations to base off of what we think reality is, what we think works, so that we can collect data of a certain type of collision. So when you test it in real life, if you see a difference between that, you know that there's going to be something that we don't understand, something to add to the standard model. So this is impossible with our computers. If you think about it, the LHC consumes about 1,000 gigawatt hours of energy compared to a computer that uses 600 kilowatt hours of energy. You can basically run 1.6 million computers for running the LHC. But also, we need something to base all of our real-life testing data on. We can't find discrepancies within testing data because the anomaly is already there. There is no standard model to compare against. So the computer is essential in this process. Computers are what will lead us to the future. Thank you.